Okay, good afternoon, everyone. Let's get started with EfficientML.ai, lecture 4 about pruning and sparsity. So this is the second lecture about pruning and sparsity. Remember, in the last lecture, we tried to prune the neural network and show the demo. We can make it 90%, remove 90% of the parameters, and after fine-tuning, we can still while maintain the accuracy. So in this lecture, we are going to continue talk about pruning and sparsity. So lab 1 is released today. So that will be the first lab, which will be on Google Colab. So if you click the link to the homework, make sure you select open as Google Colab rather than open as text editor. If you open as text editor, it will show random different only text only. So make sure you open it with Google Colab. This lab should be completed without having to buy a pro version of Google Colab. Should be able to finish in reasonable amount of time. So, and you can reference our demo in the last lecture if you have any difficulty trying to finish this lab. Okay. All right, so neural network pruning, what have we introduced so far? So last lecture, we talked about pruning a neural network. We can either remove its weights, the synapses, or we can remove those neurons, right? Making a dense neural network to become sparse. Okay, and we can have different patterns, different granularities of pruning, and also have different criteria of which weight to remove. Okay, so let's review a little bit. So pruning is natively supported. Pruning and sparsity is natively supported in NVIDIA GPUs, getting a lot of traction in the recent few years. The definition is basically make the original weight to remove lots of them, remove some of the weights to set them to be 0, so that those non-zeros should be smaller than a threshold. Okay. And we can have different granularities of pruning. We can have fine-grained pruning, which give you the maximum flexibility, but hard to accelerate. And also we can do coarse-grained channel pruning or kernel pruning, which give you certain structure, but you can prune less. But it's easy to directly accelerate it to get the measured speed up, even without using specialized hardware. We also talk about how to select the synapses to prune, which weight, how do we determine which weight should we remove? Okay, so very important based method, very practical method is the magnitude-based pruning, right? Just select the pruning candidate based on the absolute value of that weight. Okay, say, well, these are the 2 largest values, then we keep them. And these are the small values, small weights, then those are the candidates that we are going to prune. We also talk about the criteria to select which neuron to prune and the relationship between weight pruning and neuron pruning. So remember, what's the relationship between pruning the neuron versus pruning the weight?
Pruning the weight is pruning synapses, so removing connections between neurons, whereas pruning neurons means removing the node itself at all. And I think they translate differently to accelerations in different hardwares.
Yep, very good, very good. If you remove the neuron, all the weights connected to this neuron will be removed. Basically, the weight matrix, you basically remove the entire row. Versus for convolution, you can remove one of the channels, the filter, the weight matrix, you are removing like this row and this row of the entire kernels. Okay. So let's continue the discussion about how do we determine the pruning ratio. Okay, you can imagine you have many layers in the neural network, right? should we prune them uniformly, or should we prune some of the layer more, like here, versus some of the layer we prune less? And how do we determine that? How should we find those per layer pruning ratio? So we can see there are two different methods. Uniform shrink, right? The advantage of this one is very easy, okay? Versus we can choose different sparsity for different layer, right? So we tried the latency versus the accuracy, okay? So ideally, which point would we ideally want to achieve? Which corner? Left top, right? So this is what we want to achieve. Pretty fast, low latency, and also high accuracy, right? So we can imagine the lower the latency, also the lower the accuracy. So that's as expected. We start with the full network, which is right here. If we uniformly scale down the channel of each layer, you can see the gap gets faster, lower latency, but the accuracy also gets slower. But if we do some smarter way to smartly select different ratios for different layers, we can get a better trade-off curve between latency and the accuracy.
Sorry, just to make sure I understand, when the different shrinkage is different shrinkage for different channels within the same layer, or for different layers of the network?
For different layers of a neural network, like this is a 5-layer neural network. Now we are shrinking them like this is like 0 to 100. This is the uniform shrinking ratio, but this one you are pruning more for this layer, you are pruning less for this layer.
So then what do you mean by channel? I thought channels were within a layer, there are multiple channels.
Right, and you are pruning a certain number of channels. Like here is 100 channels, now this is only 30 channels. Good question. Okay, so how should we find the ratios for each layer, right? How should we determine, oh, this one, we should prune it more. This one, this channel, we prune it, this layer, we prune it less. Hey, so I designed a method called a sensitive analysis. Try to analyze how sensitive are you, is this layer with pruning, right? For certain layers, if you prune just a little bit, the accuracy drops very drastically, versus some of the layers, like the fully connected layer, even if you prune a lot, the accuracy still maintains the same. Okay, so in that case, which one should we prune? Yes, the fully connected, the bulky, the large layer, but also it reduces the accuracy, relatively less sensitive. Okay, so let's see what is a sensitive analysis. So just use AGG 11 on Cypher 10 dataset as an example. So we pick a layer in the model, okay, like layer 0, and we plot a chart with the x-axis to be the pruning rate. How much did we prune? Starting with no pruning, which is here, versus we prune 40%, 50%, 70%, 80%. Okay, so this is the percentage of weights that got pruned away, right? So this is the accuracy. So you can imagine how should the chart look like? Does it look like this? Look like this? Right, it should decrease, right? The more we prune, the less accurate we get. Okay, so this is exactly the case. Starting from layer 0, the higher the pruning rate, the more we prune, just like what we did in the demo in the end of last lecture, the more accuracy loss. Okay, so by pruning away 90% of the parameters, we lose like 70% of the accuracy. Okay, so this is as expected. And in the middle, we have a step size of roughly 10% from pruning away 10%, 20%, all the way to 90% with a step size. And we can choose another layer and plot the same curve, keeping the first layer unchanged. Okay, we can do it for the next layer, the next layer, the next layer, and the purple layer. Okay? So given this chart, which layer should we prune more aggressively?
Layer one.
Right. The R1, which is this green curve, right? So it is very insensitive to pruning. Even pruning away 90%, the accuracy degradation is pretty small. Okay, but is that the sole criteria? Is there a catch behind the rock?
I just have a question. So for each of those points, like for example, let's take the 20%, which 20% would be taken away?
Oh, that's from the previous lecture. When we talk about the selection of the pruning criterion, right? It's based on the importance. It's based on the magnitude. Right? We select the smaller ones to prune. So you sort them, and you first calculate the magnitude, and then you sort them, and then you prune away those smallest 20%.
So it's always like the best case scenario.
That's our heuristic. So sort it by the magnitude.
Yes, but just back to the slide.
Back to the slide here.
If I'm not mistaken, each of these accuracies are, what we're doing is we are only pruning that layer without touching any other ones.
Right.
And that means like looking from this chart, it seems very safe if we prune 50% for everyone, but we don't know what would happen after the action.
Very good point. So that's one catch, right? So here we are assuming different layers operate independently, and they're not interfering with each other. So each one we are pruning just one particular layer, assuming they're independent. However, they might interact with each other. If you prune away layer one by 50%, the sensitivity of this green curve may no longer be like this, right? So that's one catch. The reason why we did this is we have to trade off how much experiment, the GPU hours we want to do, how many points we want to evaluate versus the accuracy. Right? So that's the first catch. Is there another catch? Are we certain we should prune this green curve, a green layer? What is missing here? Remember, our goal is to balance between the computing, the accuracy, and also the model size. So far, we don't
know the absolute sizes of the layers. So 90% of layer one might be smaller than 10% of layer 0.
Exactly, right? So we don't know the size of each layer, right? So the green curve, the green layer might be a super tiny layer. It may have only 10 parameters, right? Even if you prune away 80%, you just get rid of 8 parameters. But versus if this blue curve is a huge layer, even if I prune 20%, it may already reduce a large number of weights and flops, right? So that's the second thing we need to consider in practice. However, the good thing about recent large language model and transformers, the good thing is that each layer is very homogeneous. Okay, for example, Llama 7 billion parameter model has tens of layers, but each layer they are using the same structure, same dimension. Okay, the projection, the QKB, the expansion. But the bad thing is for convolution neural nets, the size of a different layer can differ very drastically. Okay, so make sure we want to take into account not only the accuracy, but also the model size. Okay. So for simplicity here, okay, we just assume we want to prune away those less sensitive layers, assume they are roughly similar in the size, maybe differ by 2 or 3 times, but not 100-time difference. So this is very sensitive, and we want to have a threshold for different layer to have the same loss of accuracy. Again, this is just pure engineering heuristic. We set a certain threshold, and then we select the pruning ratio by this threshold. When it is above this threshold, I should, for example, for the blue layer, I will prune it here. Okay? For the red layer, this is already below threshold, so I will prune it here. Versus for the orange layer, this is the ratio I will prune. Okay? So here we can find the finer granularity we do this sensitive analysis, the more accurate we can get. Like this red curve, maybe we should set a threshold to be here, but due to our size is only 10%, we have to set it here. So we are going to implement this in the homework, but feel free to propose your more advanced pruning algorithm based on not only the sensitivity of the accuracy, but also the number of parameters. You can, if you do that, we can probably give you some extra credit. So this is how we select the pruning rate. Okay. Right. This is the catch one interaction between the layers, and also how do we go beyond the heuristics? Right. This is very easy to implement from the engineering perspective, but like we mentioned, we didn't consider the interaction between different layers, but we are assuming different layers' sensitivity are independent. Okay. So we need to make it more scalable rather than this hand selection. We can, like in my PhD thesis, I have a summer to finish the pruning of resin 50, where when I was writing the paper in 2015, there's only Alexan and VGG at that time. Then resin came at 2016, 2015. So when I was writing my thesis in 2017, I think I should really include this new model architecture to see how much we can prove. Right? So resin 50 has 50 layers compared with AlexNet has only 8 layers. Right? So the design space suddenly gets much larger, and you have so many parameters need to tune. Right? So like you have a much more engineering effort. We cannot afford to have many engineers to do such model pruning. I literally spent more than a week just to tune the sparsity ratio, how much to prune for each layer for resin 50. So after I joined MIT, I worked with my students to design automated way. How do we automatically find the layer to prune so that even if you have a lot of demand, like each customer has one network, wants you to prune, you want to design the tool to serve these customers, right? So we can have an automated machine, automated agent to do this. That would be great. We want to enable not only the machine learning expert and hardware expert to do such model compression and optimization, but also enable this non-expert plus a hardware-centric AutoML to provide a push-the-button solution, okay, to derive this efficient neural net. So that's the motivation for automatic pruning to give a push-the-button solution. Specify the target accuracy loss, the target model size, and I give you a model, and I return you a smaller model. Okay. So this is the solution we designed at that time called AMC, AutoML, for model compression, where we cast this pruning as a reinforcement learning problem, where we are using the actor critique model. Okay, so we have a critique to give you the reward function. We want to, of course, the lower the error, the better. Okay, so we want to certainly that's why we have this minus sign before that. Okay? And then we also multiply that with the log of the flops. And why we do that? So we want to make sure the flop we have less number of computing, right? We want a low error and also low flops. Why log flops? So people have done this empirically to characterize the relationship between the computation, the number of operations versus the accuracy, right? And people find roughly the accuracy and the number of operations, the number of ops, which we introduced in lecture 2, is roughly forming this logarithmic relationship. Okay, so that's why we put this log in the reward function. So we also have an actor to propose what is the action for the next step. Basically, that's the sparsity ratio for each layer, and we do that layer for layer, layer by layer. Okay. And finally, we return the embedding of this pruning method, which is the batch size, the channel number, height, and width, the index, which layer number it is. So we treat it as a game, right? Each time, imagine you have a 3-layer neural network, 1, 2, 3, and then it's like you have a game. You need to have 3 actions, and each action is just to select what is, rather than selecting left and right. Here we are selecting from a continuous space, which is pruning ratio. Okay? And after you choose the pruning ratio for all the layers, and then you can get a reward, which is the accuracy. Okay? And we can repeat this process to find the optimal pruning ratio.
Shouldn't the critic also feedback into the actor to do the delay?
You mean the latency, right? So here we are using flops to approximate the latency, but the most accurate one would be to have latency right here, since we want to ultimately find the speed up.
Sorry, what is the critic is some sort of a value function or key function?
Right, give you the reward.
But shouldn't it feed into the actors and form the signal of the actor? Or shouldn't there be an arrow from the critic to the actor?
The actor directly get the embedding and feed it to the decision is based on the embedding only.
The decision is not based on the critic at all.
No, it's just based on the embedding.
So the process is not iterative, right? It's just that like we prove 1 layer, and then after that we, based on currently what the critic says, we print the next layer. It's like that, or the outcome of the critic doesn't actually affect how we are printing the last layer.
You get the reward in the very last step.
Oh,
that's when you get the reward. You have to finish the whole game.
Okay. And the pruning ratio is just from the layer embeddings.
Right.
So we just prune based on the metadata of each layer.
Right.
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 I was wondering how credit are going to perform for this kind of pruning. Like you prune a few layers, check the performance, something as simple as this.
Yeah, I think that could be a good candidate for heuristic. All right, so here compared with the blue line is when I was doing it manually. Okay, so with human experts, just me, over a week, spent a lot of efforts. I was during the summer at Stanford. I pruned it to 29%. That's the best I can get within a week of time. With this agent, we can make it 20% with the same accuracy, with only a couple of GPU hours, less than 1 day. Okay, 4 GPUs in 1 day. And most interestingly, we find some interesting pattern about the pruning ratio of different layers for less than 50, where it is 50 layers. Okay, and here we are showing for different stages. Remember, we are doing iterative pruning, right? We prune a little bit, fine tune it, prune a little bit, fine tune it again. So we are having different stages. So the stage 1, we have this is the sparsity ratio, and then we prune it more until the final stage, which is stage 4. We find very clearly this is zigzag pattern, right? Some of the layers, the agent automatically can be pruned very aggressively, like here, here, and here, versus some of the layers are pruned less aggressively. So I dive deeper to see what corresponds to each layer and find actually these aggressively pruned layers are those 3x3 convolutions, versus these less aggressively pruned layers are 1x1 convolutions. And why prune more for 3x3?
There's a lot of overlap.
There's a lot of weight actually, and also overlap. And also it's more worthwhile if you prune just one channel, now you remove 9 weights, versus a channel here, you remove only 1 weight. That's the second catch we just mentioned. Okay, so our agent is actually pretty smart, which partially solve the second catch we mentioned. Okay, the large layer, the size of the layer wasn't taken into account of when we are using the sensitivity analysis-based method. So here, we want to demonstrate some real-world application to accelerate neural network on the phone. Okay, so this is the Samsung phone this is the Snapdragon SoC inside. We started with the full mobile net, which has almost 600 million max, top-end accuracy 70.6, and runs about 100 milliseconds. So this is 2018 result. The latest result we have, even from ResNet, this is like 0.8 milliseconds. So you have an observation how fast it is from 2018 to 2023. Okay. And when we are using EMC to prune it by 50% of the flops, the speed up is less than 2x. We can also use the latency as the target, so we exactly get 2x speed up, and the accuracy is about 70.2. Versus the naive approach, we just train a 0.75 mobile net, which is basically uniformly shrinking each layer by 25%. And here we can find the speed up is almost 70%, which is lower than the AMC-based approach.
And across these 3 models, they all have like the same test accuracy?
Accuracy is in this column.
Oh, got it.
Actually, this one has even worse test accuracy.
So I have a question regarding the agent's decision-making concept. How does it know which, like, sorry, I forget the word, but like, what pattern does it prove in each layer?
So here we are using the most hardware-friendly approach, since this is running on the CPU. So we are doing on the most right-hand side.
So the channel,
the entire channel.
Okay.
So it's directly accelerated.
And so the entire AMC agent is designed to do channel pruning. And
right. But this is orthogonal. You can also use the agent to do fine-grained pruning. Yeah, those are orthogonal techniques. A question here: how do we associate this 25% of pruning with this 70% speed up? Why we pruned 25%, but we got 70% speed up? Is it too much? So here we are reducing each channel to be 3/4 of its original size. Say originally you have 100 channels. Now how many do you have? You have 75 channels. Should it be only like 25% faster? Or why we got 70% faster? Bits in GPU. Oh, that's one reason, but actually it's not likely to. This is already pretty small. Like the original size is just 4 megabytes. But even if you reduce by half, it's still 2 megabytes. So remember, how did we compute the flop of a convolution layer?
Fewer serial processes.
Fewer serial processes. So that can be achieved by reducing the number of layers. But here, the number of layers is still the same. So the reason is actually here. Remember, the flops calculation of a convolution layer has 6 terms. Okay, resolution height, the height of the picture, the width of the picture, the size of the convolution kernel, like 3 by 3, times the input channel times the output channel. Okay, so both the input channel and the output channel is only 3/4 of its original size. So 0.75 times 0.75, that's how much compute is left. is quadratic, right? That's why we get about 70% speed up. It's not linear, it's quadratic, since the computation flops is proportional to the input channel times the output channel. And both of them are 3/4 of its original size. All right. All right, let's introduce another cool method, which I really like, from my colleague, Vivian's group, also in the same period. Rule-based iterative versus progressive method to select how much should we prune for each layer. Okay, so this is the original 4-layer neural network. This is the pruned 4-layer neural network. And we want to select how much do we prune for each layer. Starting with the original model, again, this is an iterative approach. Okay, and we want to prune this layer such that, for example, this is the first layer, such that the latency reduction of the total neural network meets a target. Okay, we can specify, like originally it runs 10 milliseconds. Now I want to run 9 milliseconds. So delta R is one millisecond. Okay. For example, after we prune this amount, okay, I reached the target accuracy, target latency. And then we short-term fine-tune the model, fine-tune it a little bit, let the accuracy recover. The more we fine-tune, the more accurate, but the longer the total wait time. Okay, and then we can try this for different layers. Like the first layer, we have to prune it to very thin to reduce it by 1 millisecond. But the second layer, we just prune a little bit, then I can achieve that 1 millisecond reduction. Versus the last layer, we have to aggressively prune it to achieve that target. Okay. So there are so many different choices, all achieving the same latency. Then which approach do we choose? We're going to choose the one that gives you the highest accuracy with the same latency. Suppose this is the layer we choose. And then we can repeat. We give another 1 millisecond latency reduction from 9 milliseconds to 8 milliseconds, right? And then we repeat this process to find the next layer to prune, and how much do we need to prune, and we repeat this process. Finally, we do a long-term fine-tune. Since now we find the final model, then we do the long-term fine-tune to recover the accuracy and get the final small model. So here, this is again compare the latency versus the top line accuracy. This is just multiply it with like a fixed number like 0.75 versus if we do such net adapt approach, we can make it 70% faster with 0.3% higher accuracy here. All right, so that concludes how to determine the pruning ratio. We introduced 3 methods. One is very easy to implement, the sensitivity analysis based approach, just to see how sensitive the accuracy is, but ignored the size of the model. And then we introduced the two automated approach. One is AMC using AutoML. The other is the net adapt method. Okay, let's take a 5-minute break, and then we jump into how to fine tune the model.
One.
He just gave us something. I don't know if it's I don't know if yeah, I don't know. I feel like it's impossible to have like
All right, folks, welcome back. So far, we talked about how to determine the granularity, the pruning criteria, the magnitude based on pruning, how to choose the pruning ratio. Now we talk about how to fine-tune the pruned model to recover the accuracy. Okay, how should we improve the performance of this sparse and pruned model? Okay, so after pruning, we can see usually the accuracy drops, especially for larger pruning ratio, the accuracy drop is actually pretty significant. So fine-tuning the model helps recovering the accuracy. So during fine-tuning, we want to just quick question: how should we change the learning rate when we are fine-tuning the pruned model? Why should we decrease the learning rate, or should we increase the learning rate? Since the model pretty much already converged, right? So compared with an untrained model, or it's a model trained from scratch, this is pretty much converged. So usually you want to use smaller learning rates, like 1/10 or even 1/100 of the original learning rate to fine-tune the pruned model. Okay, and usually, if you want to target a 90% pruning ratio, one way is to directly jump from 0% to 100%. Okay, a big step. Versus you can do iterative pruning. Each time you prune 20%, and then 40%, and then 60%, and then 70%, and then 90%. Okay, so usually these kind of iterative pruning give slightly better results. Prune it, and then fine-tune the remaining weights. Do a little bit more pruning, and then fine-tune the remaining weights, and then 70%, and then fine-tune the remaining weights. Certainly, this is difficult to be automated. Like you have to restart the pruning and also sensitivity analysis and also retraining for each step. So from the implementation or engineering perspective, iterative pruning requires more engineering effort. So we actually implemented just one pass of pruning if limited by user experience. So for research, or if you just have one single model to prune, highly recommend you use this iterative pruning approach. So that's the difference between doing academic research versus putting something into a product that can fit many different customers and diverse neural network structures. And another challenge we face when making a product with this pruning algorithm is the bypass layer. Since the bypass layer have this dependency, like a tensor times plus another tensor, they should be of the same size. Otherwise, you cannot do element-wise add, like the bypass layer widely exists in Resident 50 or MobileNet, whatever, right? So we have to do some tracing to find those dependencies so that we can observe those dependencies. You can still apply those bypass layer. So that's why in the homework, you will find it pretty simple because there's no bypass layer. So if you want to challenge yourself and want to prune a neural network with bypass layer, it will be very fun to do. And during the retraining process, we want to add different regularizations. Okay, so first of all, we want to penalize those non-zero parameters. We want to encourage as many parameters as to be zero as possible. Okay? And also we want to encourage smaller parameters. If it is small, it's likely that during the next iteration of iterative pruning, they will be pruned. Okay, so the most common regularization for improving the performance of pruning is using either L1 or L2 regularization. Okay, L1 regularization is just add lambda W absolute value of W Out regularization is just lambda W square. Okay. So very popular. These are very popular regularization functions, but certainly there are lots of research on different heuristics, different regularization functions. But in practical, if you want to make a product or make a startup or something, this is the regularization function to go. Okay, so that pretty much completes the algorithm part of pruning from finding the granularity criteria, pruning ratio to fine tuning. And now I want to introduce an interesting paper called the lottery ticket hypothesis. So people ask, we have to train the model to converge and then we prune it. Can we start with a sparse and prune the model, directly train the sparse model to begin with? Can we match the accuracy compared with training the dense model? Is that feasible way? Is there a catch? Is there something we need to take care of?
Isn't that dropout?
So the difference between dropout is that the motivation for dropout is to prevent overfitting. So at each iteration, we are removing randomly different weights, right? So here, the pruning is that we want a fixed model at inference time that we can speed it up.
I think the answer is no, because in higher dimension, it's easier to model the data. Then you can remove the dimensions, kind of like projecting lower dimensions, versus to start with lower dimensions, then it's very hard.
Very good point. So actually, we find for this larger neural network, redundancy is very crucial for you to converge at a good local minimum, since we are using convex optimization, which is SGD or its variants, to deal with a highly non-convex problem, which is neural nets. So over-parameterization and redundancy is quite crucial. Okay? But this is very interesting paper explored for certain cases, like for CIFAR, for MNIST, these relatively simple tasks. It is possible to start with a sparse neural network. But how to find the sparsity? You still have to train it to converge. Okay, so you train it to converge and then prune it based on the magnitude. Okay, so you get a sparsity pattern, whether you prune the first weight or the second weight. At the starting point, you don't know whether you want to prune which one to prune. Okay, only after you train it, you get the magnitude, you know which one to prune. Okay, and you use that sparsity pattern. So you only inherit the sparsity pattern from there to here, okay, rather than the weight. The weight is still randomly initialized. That's why you see the color here is light blue versus here is dark blue, right? So just use the sparsity pattern, but use randomly initialized weight. It is possible to train the model to converge at good accuracy for CIFAR and MNIST data set. But for ImageNet, this is very challenging. This is still active research. How do we get rid of this training process and directly get an idea which one to prune? People find maybe after 3 or 4 epochs of training, that's enough to find the sparsity pattern, but still that's not zero. Okay? Can we start with something that is very sparse and pruned, but still unsolve the problem? Okay, so now let's talk about system support. Why do we need system support? Like in the last lecture, I had a very good question. We pruned the model to 10%, by 90% to only 10% of parameters left. But the latency, the speed of the training is exactly the same. Didn't get any speed up. But how do we get the speed up? The first approach is, of course, use coarse grain pruning, prune at the filter level. So you remove the entire row of a matrix. So you can still use the dense matrix multiplication library to accelerate it, right? But the caveat is that the pruning ratio is less. Remembering the different granularities, the left-hand side gives you the highest pruning ratio. And how do we utilize that? I'm going to introduce the system and hardware support for sparsity, so you can turn those flops reduction into measure the speed up. I'm going to introduce 3 lines of work the efficient inference engine that takes advantage of weight sparsity and activation sparsity. And then the NVIDIA Tensor Core that takes advantage of 2 to 4, or in general M2N weight sparsity. Finally, torch sparse point accelerator to take advantage of the activation sparsity. Let's start with the weight sparsity and activation sparsity to give a full picture. So rather than directly inference the model that was trained, we want to first compress the model. Make a large model to be small and sparse, and then we run inference. The simple knowledge is just 0 multiplied by anything is 0. Okay? Anything, if the weight is 0, then you don't have to multiply with the activation. If the activation, say after value is 0, then you don't have to multiply with the weight. And the third principle is that neural network doesn't have to be precise. You can quantize it, you can approximate it, which we'll cover in the next lecture. That's the next project. That's the next lab as well about quantization. For now, let's focus on these 2 parts. So we find we can prune the model by 90% leaving only 10% of the weight. So that's this weight sparsity, which is static. No matter which input it is, the sparsity pattern is exactly the same. So we can get about 10x less flops or less ops, 5x less memory footprint. Why 5x? What is missing? Where is the other 2x?
Like there's overhead to store like the indices of the non-period.
Exactly. So in order to represent the sparse matrix, you want to have the index to tell you where am I, right? I'm a non-zero, but am I in the first row or the second row? Okay, so we need the index to tell you where is the location is. So that's the overhead about 2x, roughly 2x. Depends on the precision you use, but can differ. And then we have the sparse activation. So after value function, we find roughly between 60 and 70% of the activations becomes 0. Okay, so we can doesn't have to multiply those 0 activation no matter which weight it corresponds to. However, this is dynamic. You don't know at runtime for different input image, it may have completely different sparsity pattern. So we save about 3x compute. 30% corresponds to roughly 3x. Hard to actually save the memory footprint. And finally, weight sharing, and we can quantize the weight. So only 4 bits, only 16 choices. So these two, we can approximate them by the same number. They share the same weight. That's why we call it weight sharing. So that saves 8 times memory footprint if we represent the weight to 4 bits compared with originally it was represented with 32 bits, which we're going to dive deeper in the next lecture. So these are the 3 principles we can apply. Even as this is like 2015, but even 8 years later, this is still the principle that we can apply to modern neural networks. Even for large language model, pruning, quantization, those are still a very popular approach to accelerate them.
Sorry, but can you clarify again on what does weight sharing actually does? It seems to me that this is currently now just a low point score instead of a FP32. So is there, like 4-bit is definitely not enough precision, I assume, for a model. So where do you get?
Oh, yeah. So yeah, I'll dive deeper. That's the content for the next lecture. But in summary, in short, we don't have to choose from many different numbers, 2.1, 2.1, 2.2, 2.3, which we can directly jump from 2 to 3, right? So we can use integer numbers to represent them. And also we can still use floating point, but use a limited number of floating point numbers, like using only 16 floating point numbers. So you need only 4 bits to index into those 16 values. And actually that's the lab 4, which we are going to implement to accelerate Llama.
are these in isolation, like the 10x and 3x, and do they compound when you combine these? Is it 30x, 40?
Yeah, that's a question for you guys. Can we combine these savings, or they are mutually exclusive or non-exclusive?
I think the limit coverage is not linear, so you cannot draw it.
Yeah, I don't see you can do like 2 times times 3 times 7 times, but I think like you could probably do it at the same time, right? I don't see anything stopping it.
Right. Don't see anything stopping this, right? You can multiply A with B, right? So you get rid of 90% of A and you get rid of 30%, 70% of B, right? So altogether, if anything, it's not like both A and B has to be 0, then you ignore it. But either A and B or B is 0, ignore it. So you can multiply these together. And similarly, the weight sharing is showing fewer number of bits per weight. But here you are having fewer number of weights. Right? The number of weights get reduced, and the precision, the number of bits per weight, also reduced. So we can multiply them together. So these green part is also multiplicative.
So the principle limit here is like the fidelity of each unknown fidelity model after each operation, right? Since we can't really know the impact, and just we can't really know how well it's stacked up well maintaining an accurate model.
So the question is whether this recover maintains the accuracy. So that's a very good point. So these pruning and quantization, they both hurt the accuracy, right? So the natural question is, can we still quantize a pruned model? I'll show that in the next lecture. Actually, it's very doable. You can prune, you can quantize a pruned model. But you want to do the pruning first, and next you want to do the quantization rather than quantization first, then pruning.
At a high level, is there some risk of overfitting when we're doing a lot of pruning and quantization? Because even though we have a test set, we have this outer loop that feels a little bit like the risk feels similar to like p-value hacking in the sense that we're searching over an extremely large solution space.
So usually more parameters leads to overfitting, right? You can have like a linear function, but you are using 3 parameters to fit it. It's going to cause overfitting. So pruning naturally reduces the number of parameters you have in your model, rather than expanding the number of parameters in the model, which is leading to the overfitting journey.
But like the choice of parameters that we keep, is there a risk of that being overfit to the data that we have?
So we are reducing the number of parameters. So you are using actually a simpler model to predict something, right? So less number of parameters is what we always hope to reduce overfitting.
Yeah, I think this question is similar like overfitting in the algorithm, because like in the algorithm we are trying to find the sparsity pattern with regard to like certain, we are trying to maintain certain say testing accuracy. So if we are optimizing the sparsity pattern with testing accuracy as the objective, maybe there's a shift in the data and
yeah, that's a good point. For example, when we are selecting the pruning ratio, right? We are using a validation set to plot the accuracy drop, right? So we are touching the validation accuracy. So the rule of thumb is to use different validation set when we are doing the sensitivity analysis, rather than overfitting that with your target test set. So you shouldn't do the sensitivity analysis using the test set. Good point. All right, so let's see, how do we parallelize the computing at the same time of exploiting sparsity? Usually they are mutually exclusive. It's hard to maintain both, since for GPUs, different threads has to do the same amount of work. But how do we parallelize them? So in this example, we have 8 rows and also 4 columns in the weight. This is the input activation 1 by 4. This is output activation 8 by 1. Okay, so here we parallelize them across 4 processing elements short for PE. PE0 is responsible for this green rows, and PE1 is responsible for these purple rows. And these 4 PEs work in parallel to calculate this vector matrix multiplication. Okay, so this is logical, and this is the physically how each PE is stored those non-zero weights. And we can see for this green PE, PE0, the non-zero element as W00, first one. The second one is a 0, so we are not storing that. The direct next one is 0,1, and it's skipped by 1 element, so we have a skip of 1. And then we skip 2 elements, okay? Skip 2 elements, so this is the relative index, showing the distance between this non-zero element, W42, which is here, the distance between this non-zero element with the previous non-zero element, which is W01, okay? And there are exactly 2 zero element that is skipped. So that's the overhead we previously mentioned to represent this sparse tensor. Okay? Following W42, immediately we have W03, and then W43, which is the last one, which has a skip of 0 with previous elements. So that's the virtual weight. That's the we'll talk about it, why we call it virtual weight, because we're going to do a decode. And the relative index showing the skip, showing the distance between the current non-zero with the previous non-zero. And finally, we have a column pointer showing that which element is starting a new column. Okay? Starting a new column is W42 is starting a new column. And the 5th element, the last one, which one is starting a new column. Okay? And column pointer is usually log 2 with the number of entries. So here the rule of thumb is anything multiplied by 0 is 0, so we can ignore it. So when we are having the first activation, we find, oh, it's a 0, then we don't need to do anything. And next we find the non-zero element. Then we brought, okay, and then we multiply it with the different PEs in parallel. Okay, so the green PE, the blue PE, and also the orange PE. And then we find another 0, we skip it. We find another non-zero element. Then we do the calculation. Okay? And finally, we add the bias, pass it through the value, and complete the calculation. So this is the microarchitecture for each PE. We first have activation queue, which stores those non-zero elements. Okay? If the 0 is not in the queue. And we pass it through the even pointer and odd pointer to get the location. And then we use the pointer to access the sparse matrix SRAM, which stores those non-zero elements. And finally, we decode from 4-bit to 16-bit. Remember, after weight sharing, which we're going to talk in the next lecture, we decoded from the 4-bit into the 16-bit elements. Do the multiplication and add, and finally write it back to the activation register. And we have a linear non-zero detection unit to after feeding it with the random activation function. So the special part is we take advantage of the activation sparsity, only have the non-zero elements in the activation here. We take advantage of the weight sparsity, only store those non-zero weights, and take advantage of the low precision and weight sharing to decode from 4-bit index into the 16-bit actual weight. We are going to implement such a decoder in our Lab 5 so that we can run Llama 2, which has 7 billion parameters, but the weight only occupies 3.5 gigabytes, which can fit your laptop. So this is the accuracy when we are quantizing using choosing different precisions. So 16-bit integer with very minimal loss of accuracy. And here is the flops reduction. So the weight is 9% of its original size. Activation is 35%. Since either one of them is 0, then you can skip it. That's why we can multiply them together to get the actual flop reduction. So 10%, one third is roughly 3%. So that's 33x. Okay, so this is the IC layer of LX, nav, VGG. But pay attention to this neural talk, which is LCM. Okay, so for LCM, they are not using value activation. Okay, that's why here the activation density is 100% is dense. So the saving only comes from the pruning of the weights. Okay, so that's the RN and LSTM for image caption. For large language model, the pruning is far behind this 10x because fine tuning is pretty challenging, and we are still trying to figure out a way to do that. So if you're interested in that, we can discuss that in the final project. So this is showing the throughput, pretty good speed throughput, energy efficiency. And actually this paper was listed as the top 5 most cited papers in the 50 years of ISCA, which is, ISCA is a international symposium on computer architecture. The first one is in 1995. The 2017, this is in data center performance analysis of TPU. This is the Google's TPU paper. And the framework for architecture level power analysis and optimizations, transactional memory, and EIE, which is the first one, introduced the weight sparsity and weight pruning, and to accelerate it with specialized accelerator. Although these two pieces of work is pretty new, but over 50 years of ISCA, this kind of machine learning accelerator is gaining a lot of momentum in recent years, compared with these old topics. So there are also pros and cons. So this year I wrote a retrospective paper. Basically, the committee invites those papers to write after a period of time, like after 7 years. What are the pros? What are the cons? What are lessons learned from this work? Okay. Of course, one difference is all the authors previously all Stanford affiliation. Now they are everywhere, except for our advisors, Mark and Bill. They still have their old affiliation. But all the students now they're at MIT, some of NVIDIA, CMU, Google, Samsung, everywhere. So the pro is that EIE basically says specialized hardware can make it faster to do sparse operations, even the density is roughly 50%. Okay, and there's opportunity in both the weight sparsity and also the activation sparsity, where we can exploit. We can save the energy. We can not only save the energy by skipping the 0, but also saving the latency to not spend the cycle to compute on it. And also aggressive quantization from 4-bit using weight sharing, which we're going to talk about in the next lecture, can save memory footprint and decode it to 16-bit. So conventionally, the memory and compute, they are using the same precision. If it is 8-bit, then you store it in 8-bit, you compute it in 8-bit. But here, EIE basically says you can store it in 4-bit and compute it in 16-bit because memory is expensive, computing is cheap. So we can afford to use only, we can use 16-bit to do computation, but we have to use less number of bits to do the storage. And actually, we are going to show, implement that in lab 4 and 5 and show we can deploy Llama 2 on a laptop using this approach. Since Llama 2, lots of language models, real-time text generation, they are memory bounded. So we're going to talk about this W4, 4-bit weight, A16, 16-bit activation in the next lecture. EIE is not ideal, okay? EIE isn't easily applied to an array of vector processors, so the parallelization capability is limited. We can use structured sparsity to conquer that. I'm going to introduce next. And also there's pretty big control flow overhead. Okay, you want to do one arithmetic operation but you have to do a lot of redundant operations, and also I have to store those indices. EAE only support FC layers. Doesn't at that time it didn't support convolution layer. But interestingly, from last year, with the big explosion of large language model, they are all FC layers. So this is not necessarily a con. So fit everything in SRAM, that's the assumption for EAE. Actually, TPU was designed to have 28 megabytes of SRAM. Why is that? Because the weight has 14 million parameters. So that's into 8, that's exactly 28 million parameters. So actually, many commercial chip design used SRAM to fit all the weights, including Cerebras, which designed a giant chip, has a giant SRAM to fit many weights on it. So yeah, it did have a quite influential in industry, but this is perfect for tiny ML. Many vision applications, we find we can perfectly fit all the weights in on-chip SRAM. But for large language model, so far, as of today, maybe next year it will change, this is still challenging. 7 billion parameter, you need 7 gigabytes of SRAM, that's still quite expensive. So we generalize a few principles of efficient AI computing. Right? So what is the principle? You want to be lazy. You put a 0, skip it, don't compute on it. Try to avoid those redundant computation, okay? And quickly reject the work or delay the work. If it is 0, just reject it, don't do it. Or delay it as much as possible, okay? Which has opportunity in like generative AI, you have spatial sparsity. Like when I'm editing a photo, maybe only edit 10% of the pixels, then why bother to generate the remaining pixels? Okay, so reject the work. I'm going to talk about in the middle of this, this course. And also transformers, there's sparsity in the token level. Not each word is important, right? You can mask 20% of a sentence, you can still get the meaning. Okay, so token level sparsity, you can also do progressive quantization. Okay, start with 8-bit, just try what is the softmax distribution. If it is already pretty sharp, then you don't need to, start with 4-bit. If it is pretty sharp, you don't need to do the remaining 4-bit. If it is pretty flat, you are pretty uncertain, then you do the 8-bit. You start with something lazy, only 4-bit. If you don't trust it, then use the full 8-bit, so progressive quantization. Also videos, there's temporal sparsity. Frame 1, frame 2, maybe only a few pixels changed, maybe only one object or 2 objects moved. The unmoved elements is sparse. If you calculate the diff, subtract frame 2 from frame 1, you can find a lot of 0. Okay, so temporal sparsity we can take advantage of. Point cloud in autonomous driving, the LiDAR sensor that is rotating on the top of a self-driving car, emitting many beams. So there's spatial sparsity. Not everywhere you have the object. So how do we compute on it? I'm going to introduce torch sparse. So we envision AI model will be very sparse. Even the mixture of expert model, okay? Like the GPT-4 is widely using the mixture of expert approach. You have a giant model, but each time you are not using all the parameters, but sparsely using a portion of them. Of course, it's still structured sparsity. It's not like this here, but it's on the other side on the granularity, which is easy to compute with dense linear algebra. But you are not working on all the weights, but a subset of the weights, okay? And various granularity and structures, co-designed with specialized accelerators. So sparse model will have a lot of imagination in the future. So the second part, I'm going to introduce the 2-to-4 sparsity, or in general, M2N sparsity. So if you have a A100 GPU or later H100, we have this capability in the GPU. Like here, every 4 elements, what is the maximum of non-zeros. So we can have at most 2 non-zeros for every 4 elements. Okay. So for this whole row, which used to have 8 entries, now we have at most 4 entries together with its index. For example, the first index for this element, which corresponds to here, should be 0, since it's the 0th. Versus for this one, it should be 3, since 0, 1, 2, 3. Okay, so we needed 2 bits to store the relative location. And how do we compute on it? So we have this weight matrix that is n by k, and this is the activation matrix. We multiply the weight with the activation, but now the weight has this 2 to 4 sparsity, has this structure sparsity. Okay, so we don't have to do all the 8 computations, but instead we select only those non-zero weights, which is only 4, compared with originally it was 8. Okay? And among these 8 activations, we use the index to select among, like from this 4, it can be either 0 to 3 for each index. So I select those non-zero elements corresponds with the same to the non-zero weight with the same sparsity pattern, right? Non-zero, 0, 0, non-zero. This is also non-zero, select, no select, no select, select. So using the same sparsity pattern to select the activations that corresponds to those non-zero weights, which can be easily implemented with the max, with the max. And then you do the dot product for only 4 entries rather than 8 entries. Okay? And you put it in the result by calculating this row times this column. Okay? So only 4 max compared with here, we have 8 max if you compute it densely. So far, so good. That's how NVIDIA GPU, the sparse tensor core, handles 2 to 4 weight sparsity. So actually, this is the sparse versus dense speed up providing result with different dimensions. Actually, the larger the matrix, the higher the speed up. So almost 2x, roughly 1.8 to 1.9 times faster than the dense version across different matrix size. And this is across different popular neural network structures. This is the accuracy, the dense version versus the sparse version. And actually, we can further quantize, that answers the question, we can further quantize the model to iterate on top of a sparse model. So we can apply sparsity and quantization together. Okay. So I have a couple of minutes. Also, I'm going to introduce some new work for point cloud, take advantage of activation sparsity. Okay. So activation sparsity. So this is a general convolution we introduced so far. Okay. You have a input feature map, the weight, the output feature map. The problem is that the more you convolve, the denser you will get. So say initially you have 5 points in the space. Like, for example, this is a point cloud or particle in the physics, or there are lots of such representations. Or if you have AR/VR device, you have a LiDAR sensor, like in my phone. My phone has this LiDAR sensor here. It emits a lot of beams and collect few points. If it gets reflected on an object, but if there's no object, it'll be 0. Okay. So we want a feature map after each layer to maintain those sparsity patterns. So if it is non-zero, it is still non-zero. But if the object is 0, we want to make it still 0 after doing the sparse convolution. Okay? So the sparsity ratio maintains no matter how many convolutions you do, rather than the more you do, the denser you get. So let's see. The original convolution produces one one output for each window. Okay, so like there are 9 elements, but for sparse convolution, you only calculate when the output is non-zero. It corresponds with the same sparsity pattern as the input. But if you move to here, there's nothing here, so you don't do any computing. So this gives the difference among these 9 elements. So 100% of them needs to be calculated for dense convolution, but only a subset of them needs to be computed for sparse convolution. Since out of this window size of 9, only 2 of them needs to be computed. So for different weights, like weight -1, which is actually corresponding to this location, only 2 inputs interact with them. Okay, and for -1, 0, only 1 element interact with them, or 5. So this is highly imbalanced. Different weights interact with different number of inputs. So how do we parallelize such pattern? So we want to add some redundancy. We want to pattern them so that they're of the equal size. So we waste some of the computation, but which buy us some regularity. Okay, so I can parallelize them using the same batch matrix multiplication. Okay, so that's the principle here. One important principle to treat computation for regularity. I pay some redundancy to calculate on zeros, okay, but I get the regularity, which makes me easy to parallelize, especially on GPUs.
Sorry, maybe I missed it, but so you're able to speed up the convolution operation, the matrix multiplication there, but in terms of the number of non-zeros at the output, there's no way around that. At least we haven't talked about it, right?
Right. I actually did a lot of computing on zeros. So I'm wasting a lot of cycles.
No, but in the previous step, this non-zero dilating, what
for,
to make them not dilate?
For that one, the way we make it non-dilate is by enforcing the output to have the same sparsity pattern as the input. So even if you calculate something here, you make it 0, so that the next layer is a sparse input. Okay, so in comparison, the baseline approach, you don't waste any cycle. You have only calculated on non-zero elements, but it's very irregular, very difficult to parallelize. So overhead is pretty good, no overhead, but computation regularity is pretty bad. Or we can batch everything together to pad a lot of zeros to make it a dense convolution. So lots of computation overhead, very bad, but regularity is super good. You can parallelize the whole chunk of computing through it to a high throughput GPU. What we did here is computation with a grouping. A group some of the similar matrix sizes to pad only a little bit, and group these together, group those small matrices together, and launch 3 GPU kernel cores, which is a good balance between the computing overhead and regularity. All right. With that, let me, since we're pretty much out of time, do a quick summary of today's lecture. A lot of animations for hardware design. You can cover them in the future lecture. So we introduced automated way to find pruning ratio and the lottery ticket hypothesis to find, it's actually hard to find the sparsity pattern without training, and introduce the system and hardware support to turn those theoretical saving into measured speed up. And in the next lecture, we'll talk about numerical types. Like you have heard, what is a transformer engine, FP8. Those new representation of the number will give you a very detailed introduction. What is FP16? What is int8? And also how do we quantize neural networks, which lay the foundation of our lab 4 and also lab 5 to implement Llama 2 on your lab. Okay, so have a good day and good luck for the lab 1. Absolutely.